All right, and here we go. New chapter, chapter 4. We're going to break into two parts. So you can see here, part 1 will be made up of the first 4 sections of the chapter, 4:1 through 4:4. Throughout both parts, basically, we're going to look at, just focusing on the first one. I guess that's what I got the big ideas set up for here. Really getting into some graphs, some higher degree, which we'll talk about here in a second, degree polynomials, and then focusing on just some operations among polynomials. Okay, add, subtract, multiply, and divide polynomials. So that's the chapter, the first part of the chapter kind of breakdown. Today specifically, these notes are for lesson 4.1 on graphing polynomial functions. All right, so that term's come up a few times. We got to talk about what the heck is a polynomial function, being able to identify one. And then the second part of the lesson involving end behavior of a graph of a polynomial function, and how we'll go through that process of graphing them. Okay, so the first parts we're all adding to our notes. It's a little bit of vocab. First things first. All right, so I've mentioned polynomial, which poly is a prefix for many. Mono is just one, right? Single. So before we start talking about polynomials, let's talk about monomials. A monomial is a single term. It could be a mix of number or number and variable. We can have exponents involved, but there's no addition or subtraction going on. Okay, so that's when I say single term. That's kind of what I mean, that we're not separating through multiplication. So these are all examples of monomials. The degree of a monomial is based on the sum of the exponents. So like right here, there's no exponents, so that's why, or I'm sorry, let me back up. The degree is based on the sum of the exponents on the variables at that monomial. So right here, because there's no variable, the degree on that, the power on that variable, which doesn't exist, must be 0. Okay, let's look at this one. I wish I could point better. There's like a little 1 here, right? X to the first power. So that's why this is a first degree. The one that people get, and this one's 5th degrees or 5th power, so that's why that's 5th degree. The one that people get confused with is right here, in that they see the 2, but the A also has a little 1, a little first power on it, so that's why it's saying 2 plus 1. The degree of this monomial would be 3. Okay, don't get hung up on that. We'll, for the most part, be working with terms that just have a single variable at it, like that. Okay, so that's what a monomial is. It's a single term, some multiplication on their positive exponents. Let's look at some not monomials. Okay, because sometimes it's helpful to just see, okay, well, these are all monomials. What the heck? What's not a monomial? Anything involving addition or subtraction. Okay, so this first example is basically saying, all right, we're taking this monomial 1, like 5, this monomial x, and then adding them together. That's actually what we're going to call a polynomial. So that would not be a monomial. And then these are kind of like our deal breakers. Anything that puts a variable in the denominator of a fraction, nope, not a monomial. Anything that puts a variable as an exponent, right? These exponents are all 1, 1, 2, 5. Anything that puts a variable in the exponent that's kind of a deal breaker for us. So we say, no, not a monomial. And then anything that has it's got to be a whole number. So we can't have negative numbers. So that's different. Whole number is different than integer. Integers do include negative. So anything that's basically not a positive counting number, or I guess it could also be 0, but no negative numbers, no decimals as an exponent, no fractions as an exponent. Those are all kind of deal breakers, okay? All right, so that's monomials. And we kind of introduced it right here. So if that's monomial, the name of the lesson is graphing polynomials. It's basically many monomials, or more than one, okay? So a polynomial, for the most part, that we're going to work with is going to involve, the definition, I guess, would be like several monomials added or subtracted. Okay, so this middle part of the table, don't get super hung up right here. We should add, I think the rest of this, add this to kind of your notes as a heading here. Common polynomial functions, make it as like a table. We got to know these words here. So the type is based on the degree, and then I think the examples here are pretty legit as far as just seeing what it looks like. So the first one, constant, we've worked with that really early on. Remember this f of x, don't let that throw you. This is like y equals negative 14. These are all like remember f of x means output. Traditionally, we associate output with y when we're making x and y tables like we will do later today. So the output is equal to negative 14. Right? That's the only possible thing. That's why we call that constant. The output is constantly negative 14. It can't be anything different. And then as the degree goes up, okay, up to 1. So if we look here, there's a first degree, second degree. So the degree, what is that based on? The degree of a polynomial is based on the highest degree of any monomial in it. And usually, like I said, for us, it's kind of just looking to see what is the largest one. The only one that was kind of tricky was here, and I said we're not going to see that a ton. This would be a third degree monomial. For the most part, we're going to see just just ones where there's a single variable. I'm not saying exclusively. We might see multiple variables at a given spot, but yeah. Okay, so there's a little bit of vocab going on there. The degree, if we want to just kind of put some of the stuff, the degree is the largest or the highest monomial degree. Notice we're not adding these all up. I'm not going like 3 plus 2 plus 1. You just look at a single spot and say, okay, this is the highest exponent I see, 3. So the degree of that would be 3. So the degree is the largest monomial degree. Kind of just looking for the biggest exponent. Other terms that come up here, I know we talked a lot about last chapter. The leading coefficient. All right, the leading coefficient. Remember, coefficients are the numbers in front, basically in front of the variables. These all have leading coefficient, or these all have coefficients in front of the variables. 1, 1, 1, 5. The leading coefficient is the coefficient. Whoops. On largest degree monomial. Okay, so the leading, if I look here, what's got the highest degree? This is first degree, so the leading coefficient would be 5. This right here has got the highest degree, so what's the leading coefficient? 2. And that kind of leads right into what's called standard form. So we're adding a little bit of vocab here for us. Standard form of a polynomial is kind of how it would officially would say. Standard form of a polynomial is, let's just say it like this to make it easy. Degree decrease from left to right. So it's getting a little bit cluttered here, but I think if we look at all of these, they're all written in what we would call standard form, where the degrees of each term decreases left to right. So 4, then 1, and then 0. 3, 2, 1. Okay, so that's what we mean by standard form. The degrees decrease from left to right. You start with the biggest exponent and work your way down. And then the last part, I know I circled it here. I just said, hey, we got to know these terms. So basically, if I see a fourth degree polynomial, the official type, what we would call it is quartic. We just got done spending a whole chapter working with quadratic functions. So that should be something that, oh yeah, that's no problem. We recognize second degree, that's quadratic. The two new ones I would think, and even linear, we did earlier on in the school year. Cubic to the third power, right? If you cube something is third degree. And quartic, I know that prefix we see in other spots for fourth degree. Okay, so a lot of vocab going on here as far as these first two parts here. What makes something a monomial, those deal breakers, which we'll look at here in a second. And then, this constant, linear, quadratic, cubic, quartic, degree, leading coefficient, standard form. Here's how all that stuff gets assessed. Did we learn that stuff? And I know it's kind of small, but I tried to keep it where we could still see it and not have to scroll across the whole page. So the first way that I would check, did you learn this vocab, is decide whether the function, so these are all functions, f of x, g of x, h of x, k of x, decide whether it's a polynomial. All right, so let's do that part first. I mean, we can go for each one. The thing I'm looking for, basically, I'm looking for any weird stuff. I'm essentially looking for any of these deal breakers that we saw right here. Do I have any variables in the denominator? Do I have any variables as an exponent? Do I have any weird exponents, not whole number exponents? Okay. So let's do that part of it first. Negative 2x to the third, no problem. 5x, no problem. 8. So is this a polynomial? We would say yep. Okay, if no, why not? We don't have to address that. Let's look here. Negative 0.8 x to the third. Yeah, that's fine. Nothing wrong with we didn't say anything. The coefficients have no impact on whether something's a polynomial. So this coefficient is negative 0.8. Who cares? Exponents are good. Again, this is just the square root of 2. It's not a great number for us, but it's the square root of 2. It's not like that's just the coefficient. It's more looking at the exponents and the variables. And then negative 12, that's just a constant, negative 12. So this is also a polynomial. Let's do the last couple, and at least this first one as I'm looking at it here, negative x to the second, yeah, no problem, 7x. This is going to be an issue for us. And it's not an issue. I mean, it's just a matter of that makes this not a polynomial function. If one of the terms, all it takes is one. This one was okay, this one's okay, but this one's not. So polynomial function, no. And then if no, why? Explain why. And we can be short and sweet. We don't have to be like big long sentence or whatever. Let's just say can't have even that negative exponents. All right, or you could say the exponent is not a whole number, right? To be kind of just like how it was written in the first part. Let's look at the next one, last one. Is this a polynomial? The x squared is fine, nothing wrong with that. But we've got a variable as an exponent. We said that's no good. Okay, so is this a polynomial function? No. Why not? Let's just say no, just to kind of word it a little bit differently. No variable exponents. Okay, so that's kind of the first part, getting into just what makes something a polynomial. You're kind of looking for the weird exponents. The only one we didn't see here would be something that, put a variable in the denominator, 5 over n or something like that. 5 over x, no good. All right, so for these ones then, C and D, this is the rest of it's all like if yes, if it's a polynomial, there's nothing to put in these. Okay, just leave them blank. You don't even have to, I'm putting little dashes in there, but you don't even have to do that. All right, so now up here, all right, we answered yes. Let's write it in standard form. Okay, we can do that. Standard form, just remember, is decreasing left to right. So make sure we write it still it's still a function. So we want to write this as f of x equals, I look at my exponents, I see 3, I see 1, I see a constant. So this one, even though it already was, let's take the time and do it. Negative 2x to the third plus 5x plus 8. All right, it was standard form, whatever. I wrote it again. Let's do the second one right away while we're kind of staying with that same theme. Now here when I look, I see a third degree, or third. 3 as an exponent, and then I see 4 as an exponent, so I actually do have to do a little switcheroo here. I'm going to try to scrunch this in here. G of x equals, this has got to come first, right? The largest exponent, so the square root of 2x to the fourth, and I'm just going to switch this to minus 0.8x to the third, and then minus 12, squeezing it in there. All right, I think we're good, right? You can do that stuff. This is negative. I just made it subtraction. This was plus. I made it positive. Everything else, the degree, type, and leading coefficient, is all based off of this first term. Once I have it in standard form, which this one we said already was for us, and this one we had to do a little bit of rearranging, everything else is based on that term. What's the degree of this first polynomial here? Right there, 3. What's the degree of this polynomial? It's right there, 4. I don't look at anything else. I don't look at this 5x and this 8. I don't look at the negative 0.8x to the third. That has no influence on the degree. The type, this is like an automatic. If you answered a 3 for the degree, that's just connected to being what's called a cubic polynomial. And then over here, a 4th degree, these are our 2 new words, would be what we call quartic. Cubic and quartic. People get them mixed up because we do Q and quadratic, right? So quartic. And then last one, the leading coefficient, that's what that stands for, LC, leading coefficient, is right here, right? So as long as we get this stuff in standard form, hopefully these are just kind of picking apart. Leading coefficient is -2. Leading coefficient, this one is the square root of 2. It's whatever term's in front. If there was no number there, I would say 1, because that's obviously implied that there's a 1 there. So there we go. All that build up to be able to identify all that stuff. What makes something a polynomial? What is the degree? First write it in standard form, state its degree, the type, and leading coefficient. Okay, we can do that. Vocab. All right. Let's move along here. A couple other things that we'll look at. So that's being able to identify. In order to graph, which we're getting to here, it's kind of the next part of it. I would say we've definitely identified polynomial functions. That's kind of that first part, that one section. The whole rest of the lesson, which you would probably think is based on graphing. The one skill we need to be able to graph here is to be able to substitute and evaluate. Okay, so when it says evaluate f of x equals da 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 da, when x equals -3, the interpretation and what I need to see is that's asking me, okay, it's saying plug in a -3. So what this looks like is saying, all right, plug in a -3 for x. Now on the left side, that's just a notation thing. But on the right side, we got to keep track of this. I know we did a lot of this in the previous chapter because that's how we made our graphs. We plugged in values. But I've seen it way too many times where we go to input this, you just like using our calculator. Especially when we're like this, when we're inputting a negative number, +5 times -3 -7. So show me at least a step on substitution. Is that Mr. Kroll being a jerk? No, I don't think so, because at least now, like, I know you can't see me, but as long as I use these parentheses here and I get stuff the way they're supposed to be, -3 to the second power, and I'm using a scientific calculator, it's smart enough that it can handle all this stuff in one. So I'm not saying we got to do this longhand and, all right, what's -3 to the 4th power and then times 2. I'm okay with us using our calculators. That's part of the class, and it's the reality of the world we live in. Like, you have calculators available to you, but we got to make sure it's only going to do whatever I tell it to do. So at this point, remember, left side is a notation thing, which we'll mention here in a second. I don't know what this comes out to, so you got to bear with me. 2 times. And if I can see them on my paper, that's the whole thing. That I'm hoping I'll use them then on my calculator. So 2 times parentheses -3 to the 4th power. I'm not pushing equals. I'm just rolling -8 times parentheses -3 to the second power plus 5 times parenthesis negative 3, and that's it, and then minus 7. So all that, crunches it. I got 68. Now, it doesn't hurt to double check. You know, I mean, could you do it longhand? Sure, you'd have to evaluate each one of these spots individually. But whatever, I think we're okay with that one. I feel like I didn't, unless I typed something in wrong. I feel like we're okay there. And then the last part, just I wanted to mention, the interpretation of why am I writing it with this f. Remember, we would say f of negative 3, f of negative 3 equals 68. The whole reason we write it like that is to associate or to like connect this notation to the point negative 3, 68 on a graph. I can see the input of negative 3. I can see the output of 68 versus just saying like y equals 68. You know, if this was instead of saying like y equals, not that we would get anything different, but the problem there is all I can see is 68. I was like, oh, what? Well, where did that come from? How did you get 68? You know, maybe you go back, you'd have to look at the original question or whatever it was. So that it's just a skill using mainly our calculator, but being able to understand how that stuff gets input. Okay, so that's how we're going to make graphs when we get to that spot, is plugging in x values. So that's something that should hopefully be familiar with us. Oh no, look at all this stuff coming up. End behavior. All right, the next new concept for us, and something that students sometimes struggle with. So make sure we add this here. End behavior of a polynomial function. I'm trying to decide like last minute here. I think, whoops, I thought these were going to disappear. There we go. And I'm not 100% sure if this is the actual page in the textbook. There's basically 4 possible things that could happen with any polynomial function, with like the beginning and the end of it. Okay, so when we say end behavior, basically we're talking about what is happening to the graph at the far extreme left and the far extreme right. Okay. Yeah, so like we said, there's 4 different things that could happen. It could fall, so like for situation 1, and there's no particular order here, that the graph falls off lower, like down and to the left, and then to the right, it goes up and to the right forever. Okay, they're like opposite directions. I could have that same situation except backwards. Okay, so now this one's going up and to the left and then down and to the right on the extremes. The flip then would be, I could have, I guess, both ends coming, you know, up and to the left, up and to the right, or down and to the left, down and to the right. Those are the only 4 situations that we would ever see with a polynomial function. That's something that every polynomial has in common as far as their graph goes. So the one thing I want to make sure I'm probably going to actually just do on a separate page here, as far as some of the notation here. Okay. So this first one, make sure we add this here. F of x approaches something as x approaches, let's just say this. Well, let's do negative first. There's a lot of symbols and arrows and what's going on here. Infinity, negative infinity. So how we need to see this, and I think this is probably the number one thing that confuses people, is like, what the heck's with this notation? For any polynomial, remember, f of x means output. AKA, for a lot of us, hopefully we connect that with y, the up and down. Okay, the output. What is it doing? Is it going up? Is it going down? And then for the arrows, we're going to say the word approaches. Oh no, I should have looked that up, how to spell that. I think that's right. Approaches for both of them. And then as x, and remember for us, for the most part, we're thinking x with input. Input. As x approaches negative infinity. So what this graph, what this would be like a question. Basically, we'd fill in that blank. This is a question like this is asking, what is the y value doing as the input, as the graph moves really far to the left, right? Where on a graph, where do the x's get close to negative infinity? Negative infinity is way, way over here. And we said there's only two things that my graph could be doing. It could be either going up forever this way, or it could be going down forever that way. So that's what this question, when it says f of x approaches what as x approaches negative infinity, that's essentially asking, what are the y values doing? What are the y values doing as the graph moves further and further to the left? As we move further and further this way, what are the y's doing? They're either going up towards positive infinity, or they're going down towards negative infinity. Okay, so that's kind of the first thing, with just some symbols and abbreviations and how we should interpret the question. You could almost read it backwards. That's kind of how I do it. As x gets really small, y gets really big or small. All right. So then the other part of this then is, okay, well, how do I know? Okay, how do I know what situation's what? There's a lot of stuff going on here. It says degree, odd, negative, what's going on here? Let's do a summary page, okay? Which I think this, I guess, would fall into that category, but here's what you want to look at. Determining end behavior of a graph of a polynomial. Okay. First thing, make sure it's in standard form. Whoops, I didn't mean to do that. Make sure it's in standard form. So let's just say make sure for the most part, they're going to be, but make sure you want to be in standard form. And I guess it doesn't technically have to be, but put it in standard form if it's not. The first thing you want to look at, and I guess it doesn't really matter the order, but need to know two things. The sign of leading coefficient, positive or negative. Okay, that's easy enough. Like, you look at the leading coefficient, is it positive? Is it negative? And then we also need to know degree, and not necessarily the number of it, but is it odd or even? So those are the two questions you're asking yourself. Is it odd or even? And then there's just certain combinations. Let's think of them like probably the one that we spent the most recently, the most time with. Everything was quadratic. So just as an example, what does every quadratic have in common? Let's just make up a polynomial here. It's going to have it has to have at some point something in it where it's x to the second power. It could have other stuff. It could have 25x. It could have minus 70. None of that stuff matters beyond just this is what makes it quadratic, right? So what does that mean for us? Well, what would this graph look like? Every quadratic graph we made either looked like this or this, right? They were called parabolas. They had a specific name. That's going to be true for every even degree. Okay, so any even degree is going to be either hands up or hands down. Okay, so you can narrow down the shape just by looking at the degree. Even degrees, and we'll write all this down here in a second. Even degrees are either hands up or hands down. How did we know? if it was going to open down, or well, you answer this one. How do I know that this graph has to look like this? Because the sign on the leading coefficient is positive, right? It's positive 1 right here. If this were negative x, now I'd be circling this one and saying, oh, that's going to open down, right? A reflection over the x-axis. So we can use our quadratic stuff, all the information we learned about quadratics, to help us now with this determining end behavior. Any even degree is going to act like a quadratic. Look at the degree. Is it even? Yeah, it's to the 10th power. Okay, it's going to be a hands up or a hands down. How do I know? Look at the leading coefficient. If it's negative, it's going to be hands down. If it's positive, it's going to be hands up. I'm saying hands up because picture Mr. Kroll standing in front of the class, putting both hands up in the air or both hands pointed towards the ground. Can we squeeze one more in here, and then we'll summarize this all? Because this is kind of a big deal. There's different things with making the graphs that, yeah, this is something we need to have a grasp on. What's the most basic odd polynomial function that we know? Probably linear, I would think, right? So just as another example, let's just call it g of x and say it's equal to 5x plus 3, right? Something that you spent probably over half of your algebra class working with was something linear like this. What would the graph of that look like? Well, it's going to be a line. Going back on some of our old skills there, right? It's going to be a line, and it's either going to what? Do this, or it's going to do this. In some way, shape, or form, right? It could be steeper, it could be flatter or whatever, but those are the basic pictures of what could happen with a line other than being flat, which would be a constant and would be totally separate. It would be a 0 degree. So how do I know what's going to determine what this line looks like? And again, it comes back to this number right here. We call this the slope, right? With linear functions, the slope of 5 means up 5 over 1, up 5 over 1. Okay, so for just this particular example, if I was going to pick one of these two shapes, I'd say this one right here is probably the best representative of that, right? Up 5 over 1, up 5 over 1. If this was a negative value, we'd be falling from left to right. All right, so I think most students have the most success, I think, when they're able to connect any odd, whether it's first degree, whether it's 17th degree, whether it's 99th degree, connecting it to what we should say here is linear functions, which is what we know because we know so much more about linear functions, and then connecting any even degree polynomial with quadratic, because we just came off a chapter where we spent a ton of time working with quadratics. Actually, 2 chapters, kind of. All right, so here's our summary. And again, I'm kind of just going to say what's said here, but try to make it clean for us, okay? Maybe using some of that end behavior summary. Let's just call it odd function. Odd degree. Odd degree function. What does that mean again? Just if you're not quite sure, something with x to an odd power. X to the 17th. Okay. The different things that could happen there. It's one of these two. Let's just draw them both. It's one of these two situations. Either this or it's this. This situation is if leading coefficient is positive. Think of a positive slope, right? Positive slopes rise from left to right. This is if leading coefficient is negative. All right, we'll get into some of that notation. I almost did it out of order here, where we kind of did this this stuff next. Whoops, thought I clicked on it. The output gets really what as x gets really small. We'll do that stuff on the examples, okay? So that's the first situation. End behavior could be of an odd. You're looking at the leading coefficient. Positive, think positive slope, think negative slope. Let's just do it right on the same one. Even degree function. Even degree function. Again, that involves something with at any point you'll end up with an x to an even power. X to the 20th, x to the 500th, right? Doesn't matter. They all have the same properties. Can we squeeze them in here? It's either going to have hands up situation. I'm just going to scroll it here. Or hands down situation. And it works the same way if, as our quadratics, if leading coefficient is positive, we'd have hands up. If leading coefficient is negative, we have hands down. All right. So I think we've kind of beat that one to death. But like I said, I know students struggle with that in the past. There's 3, 4. Basically, everything here on out is going to involve some ability to identify a polynomial's end behavior, whether it's actually fully blown making the graphs or just saying, hey, what's the end behavior? Okay. So let's kind of apply that here. Oh, what happened with that? I don't like that there. All right, describe the end behavior. So this is how this is going to be worded. And again, I know that messes with you. So let's take a look. Describe the end behavior of the graph. Holy cow, f of x equals negative 0.5 x to the 4th plus 2.5 x squared. What did we say? Get it in standard form. Sweet, it's already in standard form. The only numbers I need to pay attention to are right here. None of this stuff matters right now. So the first thing I'd ask myself, is this polynomial degree odd or even? And everybody knows the answer to that question is even. 4 is an even number. That's all I'm looking for, is that 4. So that right there narrows it down to it's either going to look like this or like this. How do I know for sure? I look at the sign right here. It's a negative number. So that we said causes a reflection over the x-axis. It's going to be this situation. So that's what I would actually do. So right now, I'm going to make that picture at least just bigger so I can work with it. That's what that graph would look like. There might be stuff going on in here like this where there's little bumps along the way. But ultimately, at the ends, it's going to do that. Down and down. All right, so what the heck is going on with this stuff right here? I know what it looks like. What do I got to answer this question for? It's the interpretation of the symbols and understanding how to kind of communicate with inputs, outputs. Let's look here. Read it backwards. Start right here. As x gets really small, as x gets closer to negative infinity, where is x approaching negative infinity? We're moving that way, right? So as we move further and further this way, what's happening to my y value, right? My outputs, are they going up or are they going down? They're going down towards what number? Negative infinity. So that's what's going in those blanks there. I'm asking myself, okay, as the x's move further and further left, and if that's where making the picture so big, it's like a no-brainer. Like, oh, okay, they're going down. And then very similarly on the second one, as x approaches positive infinity, so now as x, I'll put a little x here, as x gets closer and closer this way to the right, what are the y values doing? The outputs. The outputs are going down, 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 down towards negative infinity. So that's what's going in those blanks. It's either a positive or negative infinity. It's more just, do I understand the question? That's it. Negative infinity, negative infinity, negative infinity, negative infinity. All right, let's do a different one just to change up here. So just kind of breaking it apart. F of x equals, oh my gosh, fractions and decimals, and it doesn't matter. I see, okay, 17th power, that's the highest power. That's all I need to know. None of this stuff matters. Don't even look at it. All right. So 17, is that odd or even? Well, definitely odd. So it's one of two situations. It's either up and to the right or down and to the right. Let's see. The fact that, and then how do I know which one? I got to look at the sign of this number right here. Is 11/16? It's not a pretty number, but is it positive or negative? That is a positive number. So we kind of treat that like a slope, a positive slope. Which of these two graphs would have a positive slope? This one. So here I make this big old picture like we did on the last one. I can kind of set it up the same way as x. So here we go. As x moves further and further to the left, what's the y value doing? It's going down, 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 down towards infinity. Towards negative infinity. The flip is, as x gets bigger and bigger and bigger to the right, the y's, this is the first time we're seeing it, the y's are actually going up now this time. They're going up towards infinity, or just, you could say positive infinity or infinity. All right, so that's how we answer a question like that. Hopefully the next one, again, it's still building off that same stuff. It's just asking us a different, interpreting it differently, okay? So as I look here, I got a graph. So these are what we kind of mentioned, like the graphs might have these weird bumps in them and stuff like that, and they are what they are. We'll get into that. But what do I know has to be true about the degree and the leading coefficient? So I can't tell you numbers. Is it 6th, 7th, 8th, 9th, 10th degree? But I can tell you for sure whether it's positive or negative. That's what that question's asking. And then I can tell you, whoops, I wrote that in the wrong spot. This should be here. And I can tell you about the degree, whether or not it's odd or even. All right, we don't know numbers. We can't be super specific. But I know that any graph that has both hands kind of pointing in the same direction on the end behavior, hands down, that's just like our parabola, right? What's the degree of any parabola? It would be second degree, which second is an even. So this would have to be an even degree, right? Hands are both going in the same direction, whether they're both up or both down, that's even, like our parabolas. The fact that it's flipped over and, the traditional one opens like this, if it's just a kind of the parent function or whatever we're talking about, because this one's been reflected over the x-axis and both going down, that means my leading coefficient must be negative. I don't know. So we got to practice that stuff, obviously. The last part. So finally, it's like all that buildup, and we still haven't. The name of the lesson was what? Graph polynomial functions. Well, we finally just looked at, well, we were making some smaller generic graphs here and there. We finally just looked at one that was, okay, that's kind of a weird looking graph with that bump in it. How are we going to graph them? Okay, so here's the notes on like actually what we're going to do. The first thing, we just spent 20 minutes doing end behavior. You got to be able to identify the end behavior, because I'll show you what happens here in a second. But if we don't know that, the graphs get really messed up. You put 5 points minimum. Sometimes it's more, and we'll talk about when. How do I know when more? But 5 is like the bare bones minimum. We gotta add, and then it's a smooth curve. We're not going to make graphs that look like this. That's no good. If these were my points, if I had points here, 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 and here, I'd add a nice smooth curve versus just straight up connect the dots. Okay, let's do them. I think these two that I have here are relatively simple, but look at that. Oh my gosh, look at all those spots for x. So before we do anything, end behavior, number one thing. All right. So as I see this, I see an odd degree, right? The 3 is odd. That's the first thing. And it's got a negative leading coefficient. So that tells me, and I don't need to be super fancy, I just need to know that this graph, when it's all said and done, I usually put a little bump in the middle there because I know these third degrees are going to be, they're not going to be linear. So, but in the end, the left side of this graph should be kind of fading off to positive infinity this way, and then the right side of the graph should be falling down to negative infinity this way. And you'll see why that's such a big deal here in a second. For the most part, we're just picking x values and plugging them in, and we can probably get by with at least starting around the origin. So like 0, 1, and 2, -1 and -2. That's a good starting spot. We can kind of see what happens. Maybe they're on the graph, maybe they're not. And here's where that skill of inputting values is important. Now, zero's not bad, because what happens when I plug in a 0 here? 0 to the third power is 0, negative, plus 0 squared, plus 3 times 0. All that stuff disappears. So that's kind of a nice point for us, 0, 1, 2, 3. The downfall of this, though, of quadratic was great. We had 2-for-1 specials. We didn't have to plug in all these points. Unfortunately for these ones, we do. Okay. So I'm going to plug in 1. All right. And remember, use your parentheses. And once I get it set up for the first time on my calculator, I know a lot of us have calculators that were able to just kind of recall the last entry, like by pushing down. Okay, so that's what I'm typing in here. I'm plugging in a 1. So I'm gonna try to set my calculator up so I don't have to retype it every single time. Negative, parenthesis, 1 to the third power, plus parenthesis 1 squared, plus 3 parenthesis 1 parenthesis minus 3. I'm letting my calculator do the work. I'm taking the time to use the parentheses. I got 0. My calculator says 0. I think that sounds reasonable. I'm going to trust it. Okay. The next number I'm going to plug in is 2. Now, here's where I'm probably not going to show that, because if you could see me, I'm pushing down and I'm saying, all right, I'm going to go switch all those 1s on my last entry to 2s. So 2 in the first position, 2 in the second position, and then 2 in the third position. Okay, so all I've done is gone and replaced this with a 2, this with a 2, and this with a 2. Push equals, I got -1. So let's plot them. 1, 0, 2, -1. All right, so far so good. I'm going to replace these all. Now, this can be tricky sometimes depending on your calculator. I'm going to switch that to a -1, a -1, and a -1. Again, depending on your calculator, you might have to insert a number. So you push second, delete on my calculator that I'm using, and it allows me to insert without messing everything up. Second insert, -1, and then second insert, -1. I just got to delete the 2 that was in there. Equals, all right, sweet, -4. And for the most part, if these are all whole numbers and we're squaring and we're plugging in integers, we should be getting decent numbers on the output. So -1, 1, 2, 3, 4. Last but not least, let's go back up and switch those to -2s. 2. I like to count them so I don't miss one. 1, 2, 3, 3 spots. All right, and then my calculator says 3. So -2, 3. So a little bit time consuming, but that's unfortunate. That's kind of how we do it. So you can see right now, I think this is plenty of points. We said 5 was the minimum. What? These seem like totally random. You would not believe the stuff I've seen with these. So I think all my points are on the right spot. I like where they're at. I've seen people do stuff like this. Oh boy, that'd be really, really bad. Okay. I've seen people do this because we think, hey, as long as I hit all the points, I'm in good shape and I can add as many things as I want. What's my guide here to finish this? I'm telling you, like this people can get all the points perfect and then get here and they just see like 5 random dots on a page and have no clue what to do. Here's where this comes in. That's why this is so important. I know that I could definitely pick more points. I could plug in a -3. So when in doubt, if you're like, I don't know what to do, like how to connect these, Then start plugging in more points. Plug in a -3, plug in a -2.5, plug in a 1.5, plug in a 2.5, plug in a 3. Now, whoops, 3.3. Fine, plug all those in, and you're going to start to see stuff like showing up in between these as far as like how this graph is going to finish, but nobody wants to plug in 50 points in a graph, right? So we're trying to be efficient and not have to plug in like a million points. That's where I use the end behavior, right? I know this graph needs to come in like high on the left side, and it's got to finish low on the right side. So it's got to finish there. So I hit them in order, starting from high up here. Okay, so I'm dropping in. This is the next point to the left. I got to hit it. I must turn around. I got to turn around really steeply to hit these other points on my way down. Okay, it's almost like you've got this destination. You're starting in your car. Oh no, I thought that was gonna be a good car. That's not what I wanted it to be. And we got to hit all these points on the map from left to right. I'm driving. I got to hit this point. Oh, I got a tourist attraction way over here. World's largest ball of twine. Got to hit that one. And then we're looping back. Oh, I got to see the big ketchup bottle in Oklahoma or whatever it is, Okay, so we got to use those, and we should have arrows on the ends. Okay, don't have that part of it, but yeah, that's how we do it. And that's it. There's no follow up. There's no like identify the axis of symmetry or vertex or anything like that. It's kind of plug points, and you get what you get. So that was an odd degree. Let's look at an even one. We're winding down. I know it's kind of a longer lesson, but some new stuff for us, and I want to make sure that we hit it the right way. So here we go. I got an even, which narrows it down to either this shape or this shape. And the fact that this is a positive number out front here, whoops, makes us right here. And again, there might be stuff going on in the middle, but I know endwise, it's gonna, my car, I was gonna try to draw a better car. That's better. Is gonna start up here and it's gonna finish, there's our destination. X marks the spot. We're gonna finish over there too. All right, here we go. 0 again. Let's center it up. 0, 1, 2, 0, -1, -2. 0 is a good one to start with just because, again, it kills this term, it kills this term, it kills this term. 0, 4. 1, 2, 3, 4. If you want, maybe it's a better idea to start over here. So I would still write down, I got to clear this because I can't see it, but I would still probably write down my first one so I can see it. I'm plugging in a -2. So -2 in parentheses to the 4th power minus -2 to the 3rd power minus 4 times -2 to the 2nd power plus 4. The reason I might want to start is just maybe on my calculator, it's easier to do it that way. Parenthesis, -2, parenthesis to the 4th, minus another parenthesis, -2 to the 3rd, minus 4 parenthesis, -2 to the 2nd, plus 4. The reason I might do it to start, so this I got -2, I got 12, is on all these other ones, when I go back to it now, I can just switch this to a 1. So 1, 1, and all my spots there. So I'm pushing down, I'm going back and just switching it to 1, switching it to 1, switching it to 1. Or yeah, so it's -1 was what's actually going in there. The negative was already there. 2. Okay. But then the nice part here is when I go back one more time, I just need to delete the negatives. So I got a 1 in there. I'm pushing delete. I'm deleting the negatives. I'm going to delete that negative. I'm getting 0. And then one more round of it. If I plug in a 2 in all 3 spots, 2. And then lastly, we've got a 2. I'm getting -4. Now this one's kind of weird here with that -4 on the end. I think that's right. Seems. Let's see. Let's see what we got here. So as I go to plot these, here's what happens. -2, 12, -2 way off the graph, right? So, and you can see right here, it's going by ones. We don't need to adjust it. -2, 12, fine, way off the graph. -1, 2 is fine. It's right there. 0, 1, 4 we already put on there. 1, 0 is right here. And then 2, -4 is way down here. That one's tricky. You only end up with these 4 points, and you're like, again, I know a lot of us are like, what? How do I connect these? We took all this time, and I drew this awesome car here at the start. We know this one's kind of a clue for us. -212 would be way up here, right? So it's kind of telling us we got to come in, and we got to hit these in order from left to right. So I must have to turn my car around real quick and get up here. And then I got to turn it around real quick, and then I keep going. I see, all right, there's that one on the horizon there. I'm going to keep going to that one. But if I'm not paying attention to my end behavior and I'm just basing it off this last point right here, a lot of people are just going to say, oh, let's keep going here, when we know our destination's way up here. So this might be one that if I've still got my calculator on, I plug in a 3 just to maybe confirm it. I think I know what's going to happen. But if I switch all those 2s one last time to 3s, 3 and 3, I get 22. So the last point that I would maybe plug in is the point 322. So it kind of confirms what I was hoping was going to happen. Like, no, this doesn't keep going down. We know where our destination is. We said right away it's got to be way up here. I got to get my car turned way around. Whoops, it's probably even steeper than that, because 322, and I wouldn't be crazy picky, but 322 is like straight back up. So there we have it. Using the end behavior to help us kind of guide our graphs, plugging in points, calculator use. Last one. Oh, finally. So it's based on what we were just talking about right there. It's sketching a graph. I think this is probably the hardest one, to be honest with you, as far as just interpretation, because I know students just take a little while to kind of figure out how we're going to interpret all this stuff. But basically what it's asking us to do is, all right, sketch a graph of the polynomial that has all these things happening on it. So here's what I'm asking you to do. I tried to leave enough space. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I think that's probably enough. I'm making a really informal graph, and that's kind of how we got to do it, because this isn't super specific, but it's specific enough to tell me kind of where this graph is turning. All right, so let's take a look here. I don't know if I can necessarily go in just order and say, all right, f is increasing. So the function is increasing when x is less than 0. So remember, x, this is my x-axis, but my x's are measured left to right. So when x is on this side of the y-axis, the function is increasing, and when x is greater than 4. So that doesn't really tell me a whole lot. It's telling me it's going up in those situations, but I'm going to maybe hold off before I kind of add anything to my graph. And then same thing with the decreasing. That's basically saying, so this means let's just go back. When it's increasing, that means the graph is going up, and then this one means that the graph is going down from left to right. We read it like a book, left to right. Okay. Between 0 and 4, when x is between 0 and 4, the graph is going down. I think I actually kind of want to start with these ones right here, and maybe use them together. So the output, remember this, when I see this right here, f of x, think y value. The y value is positive, greater than 0, which means positive, when x is between -2, so between -2 and 1, 2, 3, the graph should be up here somewhere. It's above 0 somewhere up here. Okay. And then also when x is greater than 5. So I've got this point right here. When x is 5, the graph should be positive as well. So that's the first time that I added something to my graph, just because it told me that, and I use dashes because I'm not sure exactly how it's going to look, but I know it's going to be above, the y value is above 0. So here's where the y's are, above 0, between -2 and 3, and then after x is greater than 5 or greater than 5. And then this, I think, kind of jives with it, that the output, the y, is less than 0, so negative, when x is less than -2. So all these x's over here, my graph should be less than 0. and then between 3 and 5. So 1, 2, 3, and 5. So this graph is negative down here somewhere. So that I think right there gets me the majority of my shape. Let's just go back and look and see here now is where f is increasing. So it's increasing when x is less than 0. So is this graph increasing right here? Let's see here. Less than 0, all these points over here. Is this graph increasing from left to right? Sure, it's going up. 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 Now, at some point, as soon as I hit 0, it's got to stop increasing. All right, because we said it's decreasing between 0 and 4. So now I need this graph to go down. Is it going down slowly? Yeah, it's going down. It's going down. It's going down. I knew I needed to hit that spot right there. It's going down still. It's going down still. And then as soon as I hit an x equal to 4, we say, well, it starts increasing again, right? It's increasing when x is greater than 4. So this must have to turn around. Is it going up? It's going up. It's going up. It's going up. It's going up. So you kind of have to use all 4 parts in conjunction with each other. And I'd be okay if your graph had these little arrows on it to kind of like, oh, we're increasing, 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 now decreasing, 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 and then it flips over, right? So this kind of got me, this portion here kind of got me some x-intercepts. You know, it told me when we were above the x-axis, right? These are all points that are above the x-axis. This puts us below the x-axis. And this kind of tells us where those which we'll end up calling turning points are. It's increasing until we hit 0, then it's decreasing from 0 to 4. And then all of a sudden we hit 4, and then it starts increasing again. That's tough. That's tough to interpret. That's going to take practice to do. The last part then, okay, so I think my graph is in decent shape. It's at least good enough that I can answer this question. Use the graph to describe the degree. All right, hands are opposite. So the degree can't be like a quadratic. Quadratic's either hands up or hands down. These are hands opposite. So the degree would have to be odd, right? Kind of like a line, right? Our graph is doing this from left to right, right? It's from low to high. So not this one. So that means that the leading coefficient would have to be, what would this graph have? A positive slope or a negative slope? A positive slope. Wow, so that's a loaded lesson. I didn't realize I was kind of anticipating a shorter one there, and it was definitely not short. So, yeah, there you have it. I mean, that's definitely lesson 4.1. We graphed, we talked end behavior, increasing, decreasing. A lot of a lot of the lesson is weird notation for us. You know, so go back, rewatch anything that you have to. But yeah, I think we can definitely say this one's good. We've covered everything that there is to cover. So that's all I got. Lesson 4.1 in the books. I'll see you in future lessons.